So, statistical inference. What are we concerned with when we talk about inference? Well, in statistical inference, we're going to model data as observed values of random variables. And our objective is to provide a framework from which inductive conclusions may be drawn about the mechanisms giving rise to the data. So, just to bring some of this together to be clear about what we mean, we're going to analyse observed values, small x, of random variables, big X. And we're going to do so under two assumptions. Generally speaking, in inference, we're going to make two assumptions. First, we're going to assume that they constitute a random, that is, independent and identically distributed sample from a probability distribution. So they're randomly sampled, they're independent of one another, and they're identically distributed. They have the same probability distribution. Secondly, we're going to restrict this probability distribution, this unknown density, to some set thought suitable to have generated the data. So we're going to be parametric about it. We're going to have a parametric density that we believe is suitable to have generated the data. So this is the set. We're saying here that there is a joint density, the density for x given parameters theta, that depends on a finite number of real unknown parameters. We don't know these parameters, and one of the main goals of inference is to say something about these parameters, to infer something about them. So in this case, we have it's a d-dimensional parameter space. So here, the region X is referred to as the sample space. That are the values that our random variable X can take. And big omega subscript theta is the parameter space. Okay, so that's what we're assuming that our data come from. We're going to sample from that distribution, randomly sample from it. So for example, we could have X is normally distributed with mean mu and variance sigma squared. We looked at this distribution last week. In this case, the sample space is on the real line. Our parameter space, well, the first parameter mu is a member of the real line, it's on the real line. The second parameter, sigma squared, has to be positive. So in this case, theta is a two-dimensional parameter space, the first element of which lies on the real line, and the second element of which, the variance, lies on the positive part of the real line. Okay, so random, independently identically distributed, and we're going to assume the density that the data follow. So there's three objectives that are going to be the focus of inference, and we're going to deal with them in three different parts of the lecture. First, parameter estimation. So we might want to compute an estimate of one of these parameters, or it could be the parameter vector itself or some element of it, in light of the data that we have available. Hypothesis testing. We might want to test specific hypotheses about theta in light of the data. And finally, interval estimation. So compute what we call an uncertainty interval within which the true value of theta, we believe, lies. Now, I just want to put down some concrete definitions of random sampling and data, because that's what we're going to be talking about. So we're talking about a random sample, then we're talking about data. What do we mean by these? Let's start with a random sample. A random sample is defined as a collection of random variables of size n that are distributed independently and identically, that is, mutually independent according to the same distribution function, identically according to the same distribution function. So a random sample is just a collection of random variables, okay? And we talked about random variables last week, but they must be distributed independently and identically. Data are the realized values of those random variables that we observe when a sample is actually taken. So remember, we use this notation where the random quantities have got capital letters, as in big X, and the fixed quantities, or the realized values, have got small lowercase letters, small x. So to give an example of a random sample in data, and you can run this yourself in R, we're going to randomly sample 10 values from a discrete uniform distribution. In this case, x is limited to the integers 1 up to 6. So this is the example of throwing a dice. But we're going to throw the dice 10 times. That's where we get this random sample. So each throw is a random variable that can take the values 1 up to 6, yeah? And we're going to have 10 copies of this random variable. So that's the random sample. This is how we would execute it in R. We're going to sample from the uniform distribution, integers 1 to 6. We're going to do it 10 times. And replace equals true just means that we're going to allow the full number of 1 to 6 to occur each time we take our sample, each time we sample from that distribution. And when we do that, okay, I've run this in R, this is the data vector I got the first time I ran that sample in R. 1, 2, 2, 4, 3, 3, 2, 4, 4, 2. So we didn't get a 6 and we didn't get a 5. These are the numbers we got. Now this produces a data. That's the data that we got by actually taking that random sample. And these are fixed values. So this is small x. I hope that's clear. Okay, when we have a random sample and when we have data, we can then start to talk about statistics and statistical summaries. Now a statistic is defined as a function, we're going to call it big T, of a random sample. That is, T is the function T of x1 up to xn. And a statistic is a random variable which depends only on the random sample x. Now, because it's a random variable, it must be a random variable because it depends on this random sample, which is a collection of random variables. That means that the statistic T has a probability distribution, and the probability distribution of the statistic is referred to as the sampling distribution. So again, when we talk about a statistic, again, remember we're using these big uppercase letters to denote the fact that it is a function of a random sample or a function of a collection of random variables. Now, when we apply a statistic to observe values, that summarizes information contained in the data by determining key features, okay? So that's a statistical summary. So just to make this distinction clear, we want to compute the average of our DICE data by applying this function to the data. This is actually just the calculation of an average. When we apply the function, that gives us our statistical summary on real observed data. So in this case, it would be, we would add together all of our elements of our data vector, and we'll divide by n, which in this case was 10. And so the average of our data that we generated by applying the random sample, the observed values, is 2.7. Now, there's lots of different examples of statistics, and I'm sure most of you are familiar with them. And again, we'll look at these in the in-person session. And the definition of a statistic is very broad. It can include almost any data summary we'd be interested in. The only condition is it can't be a function of a parameter. 3 of the most commonly reported statistics are the sample mean, which actually we've just calculated as an average. So x bar equals 1 over n, sigma I equals 1 to n of xi. So we sum up all the values in our observed data, or all of the values in our random sample, I should say. We divide by the size of the random sample, and that gives us the sample mean. The sample variance, s squared, is equal to 1 over n minus 1. I'll explain in a minute why we have to subtract this 1, times sum I equals 1 to n of xi minus x bar. We talked last week about variance as the second central moment of a distribution, and this is how we would calculate variance from a random sample. This is the expression we would use. And we also talked last week about standard deviation as the square root of the variance, and so the sample standard deviation is simply the square root of the sample variance. So these are statistics defined in terms of a random sample. The observed values of statistics are denoted with lowercase letters, so we'd use x bar, small s squared, and s. Now, let me return to this issue here. There's an important concept called degrees of freedom, and we say that the sample variance, this statistic, has n minus 1 degrees of freedom. So what does that mean? Well, degrees of freedom that we use in calculating a statistic is the number of independent scores used in the calculation, e.g. n, minus the number of parameters used as intermediate steps. So let me explain what that means in relation to the sample variance. So let's say x1 up to xn is a random sample of size n with population mean mu and variance sigma squared. Well, the population variance sigma squared we would define as 1 over n sum I equals 1 to n of xi minus mu squared. And this is just the sample average counterpart to the second central moment. Okay, that's what we're doing here. However, we do not know what mu is, so we have to estimate mu. We have to estimate mu by taking the sample average, x bar, and so we use 1 over n minus 1 here rather than 1 over n in the sample calculation to ensure unbiased estimation when mu is unknown, because we've had to estimate it with x bar. We've had to estimate it. We've had to estimate x bar. Estimate mu with the sample mean. So the degrees of freedom then becomes n minus 1 because we're using n scores in the calculation, but we're going to subtract off the number of parameters used in an intermediate step, in this case the sample average, to approximate mu. Okay, so just to continue on statistics, the last thing I want to really say about these are to do with order statistics. So statistics such as the minimum, the maximum, or the middle, the median value, can provide useful information. And these statistics, which essentially tell us about the order of the data or the order of a random sample, are called order statistics. And the sample values, they're achieved or defined by placing the sample values in ascending order, and they're denoted x1 less than up to xn. So we place the random sample in ascending order and then calculate some simple quantities. Now, the one that most of you will be familiar with is the median. The median is the value that divides the data into two parts. Okay, so the median is the middle value of the data. But just as the median divides the data into two equal parts, we can define sample quantiles that divide the data into any number of subsets of approximately equal size. So, for instance, a quartiles of the data divide the data into four parts. We have the median, the lower quartile, and the upper quartile. So, arranging the data in ascending order from the sample minimum to the lower quartile is the first quarter of the data. From the lower quartile to the median is the second quarter. The median to the upper quartile gives us the third quarter of the data, and the upper quartile to the maximum gives us the fourth quartile. So, quantiles are simply, they're very, very simple. All it's doing is trying to describe the distribution of the data in terms of how much of the data falls in particular intervals defined by the order statistics or defined by the quantiles. Okay, that's what it's trying to do. Sometimes we use what's called the interquartile range, which tells us how much of the data lies between the upper quartile and the lower quartile. And of course we use the sample minimum, sample maximum, and the range of the data to tell us something about spread.